All right, so my name is Saurabh. I'm an engineer, backend engineer here. I'm a backend engineer here at Centred, based in Redwood City office. So I'm with the marketing campaigns data team. So our team is responsible for storing, lookup, and searching of contacts and events at a large scale. So while working on that problem, that's where we hit this issue. I'm going to talk about how we resolve fair scheduling. So before we go into fair scheduling, what is actually a fair scheduling? So it's basically like every job that you submit, it gets an equal fair share of CPU time. So when we translate this to our use case, we actually ingest a lot of contacts from thousands of users. And I want to make sure that no user is starving, one user is not starving any other user. So I want to make sure each user gets their fair share of import time. So basically, a little overview about Kafka, because I'm gonna touch Kafka as well. So Kafka, like we have a topic. So within a topic, you can have n number of partitions, and each partition is nothing but a stream of data, and it's in sequence. So anything coming later won't get consumed unless until the data before it gets consumed. So that's where the problem in our current architecture is that a user uploads file on S3. There's this Go routine that's reading file from S3 and pushing it to Kafka. And there's another Go routine that's consuming from Kafka and sending the data over to a database. So we have M users spread across N Kafka partitions, and there's a single topic. And for us, the sequence of import is important because data coming later should not override the coming early should not override the data coming later. So the sequence is important because they could be adding new contacts as well as updating the contacts. So we need to make sure the order is preserved. So the number of users M is way larger than the number of Kafka partitions. So what that causes is sometimes that if one user is uploading large amount of data, so any other users that's sharing that partition, that's where the Kafka partition comes into picture. So it gets blocked basically for some period of time unless all the user one data gets consumed. So we hear sometimes customers saying that I uploaded my data, I'm not seeing it for past few minutes. So that's when we look into it and we say that, okay, the partition is backed up, please give them some ETA. That's the workaround we have for now. And so we recently decided that we're gonna move our marketing campaigns product over to AWS. So that was a good time to start looking into various alternatives. So first thing we thought about, okay, how about we replace Kafka with Kinesis and add a whole bunch of shards in there and stream and divided one for a low-end user, a high-end user, those kind of things we thought about. So a few issues there. You only get 2 free shards per stream, so you pay for additional shards. Second is there's only a limit of 1 megabyte of data, chunk of data that you can put it at one time. So our contact record can be much larger than 1 megabyte. So then we thought about how about we put the S3 link in there. So then it comes out the same issue that, again, back to the previous problem, we have multiple files going through the Kafka stream. It comes back to the same problem. So that's when we started looking into how about we use time sharing to implement our fair scheduling. So before we go into more detail of what is time sharing, we're basically guaranteeing or ensuring that, not guaranteeing, but trying our best that each user's data get an equal share of import time. No user is blocking any other user. So this is a technical definition. I'm translating it into our use case. So this is a pictorial representation of what we actually ended up going with. So we have a dispatcher that is actually looking into S3 after every n seconds and figuring out if there is any new file that came in. So if it finds any new job, it actually kicks off creates a buffer channel and creates a pair of readers. So the first reader, what it's doing, it's streaming data in chunks from S3 and then pushing it to this buffer channel. So another routine, Go routine, is reading from this buffer channel. So the step 2 is putting one contact at a time in that buffer channel. And the second reader is creating batches of the data and pushing it to a common channel. This is a non-buffered channel. So this is using a non-buffered channel is how we are implementing fair scheduling. Because only one reader can write to this channel at a time. Also, another reason for having buffered channel on the left is because writing to database is much faster than reading from S3. So, and we don't want reading from S3 to be slowing down writing to database. Because let's take an example. If there is only 1 or 2 jobs, writing to database would be much faster. So we want the data from S3 to keep getting downloaded and being added to buffered channel, irrespective of this non-buffered channel. And once there's another Go routine that is continuously reading from this non-buffered channel and adding it to the database. So basically, I'm gonna quickly go over some of the code snippets and give you a demo of actually that it works. Just making sure I'm not leaving anything behind. So this is the main entry point. We are kicking off 2 Go routines here and then just waiting forever. So the first one is looking into S3 to pick up the jobs, and another one is writing the contacts to the database. Everything in between, all these Go routines will be created on the fly as and when a new job is detected. So this is the pickup jobs, which is, and this is not the full code, this is just the snippet, just calling it out. So here we are looking into all the new jobs, and whenever we find a new job, we actually spin up this read context from S3 Go routine. So all it's doing, and it's sleeping for every 30 seconds here. So what read context from S3 does is it creates a buffered channel and another Go routine that's reading from that buffered channel. So now it's actually downloading the data in stream from S3 and creating a contact and sending each contact to this buffered channel. On another side of this buffered channel, what we are doing is we are reading from the buffered channel. We are actually creating batch of data. So we have a predetermined batch size, it gets the contacts, and eventually once it reaches the batch size, it pushes those contacts to the channel. And if there are any leftovers, when we hit the end of file, we're just sending the remaining data over. And then it basically dies because it doesn't have any more work to do. Same with the previous one. If it doesn't have any more work to do, if it reaches end of file, we break out of it. So this Go routine lives forever. So it's just listening to the non-buffered channel, and it's reading those array of contacts, slice of contacts, and it's basically calling, adding those contacts into the database. So a quick demo. I already am uploading files to S3. I have a Fargate container running. A task running. So this is just a sample. I made sure everything is up and running. Since it picks up every 30 seconds, depends where in that time slot it is, it will pick up new jobs. All right, so it got it. So I'm just gonna look for streaming, and we cannot. So the interesting thing I found with this log is it's not deterministic, the order. Sometimes you'll see job 1, job 2, and also it also depends on the CPU. So I've given very small CPU. Sometimes it works, sometimes it doesn't work. That's why you probably see the sequence. But let me try adding 2 more files because I can guarantee it works. So eventually, when the job is done, we also clean it up from S3 so that once it goes back to pick it up, because pickup job is running every 30 seconds, we don't want any job that's done for it to even look at it. Can quickly add a few files here. So the main reason is our CPU time. It's because for the demo I created like 256, which is a quarter of a CPU, virtual CPU. Right, so while this is going on, I'll go through this and make sure I'll open up for get lessons. So first one, pipe versus channel. So if you're using pipe, you need to keep track of the record. Where's the end of record, because it's a byte, a stream of bytes. So you need to make sure you know where the record ends and then the record begins. And since we're reading in stream, concatenating the bytes and creating a record. So it's complicated. Whereas channel, they define a structure. It's much more straightforward, and you don't need to deal with all the bytes. And second one is we are using a non-buffered channel, but for fair scheduling, and there's only one reader right now reading from that non-buffered channel. It can cause throughput issues. So to get around this, you can add more writers to it. You still keep it a non-buffered channel to make sure that only one reader can write to the channel, and any one writer can write to the channel and reader can read from it. Another option is you can also make it as a non-buffered channel and make its capacity as your number of writers. But then in our use case, if we do that, we need to make sure that we are ensuring that old data is not overriding the new data. So we could use timestamps, CRDT, stuff like that. Those are other things that we are looking into to get around this throughput problem. So quickly going back and making sure it's done. Okay, all right. So as you can see here, it's intermingled. Job 3, job 4. So both factors, the log is never in sequence, and CPU. And opening up for questions.
Do we have any questions? Yeah, I'll come around.
You can run fast. Do you know how hot it is in here? This is an artisanal question. Oh, wait.
So your current implementation, then, if one of those Go channels crashes, you lose that client's import?
Yes. So what we have done is we have made it as an idempotent. So we never delete the file from S3 unless until the data goes into our database. So if anything dies, we retry the whole file. Yeah, it's a lot of updates in that case, but that's the best approach, because it's not very often it dies if your program is robust enough, but it dies. So we just took that approach that we will take that hit at that point in time.
And all of this is running in a single process with a lot of Go routines.
Correct. It's just a forget task, basically. It's all in AWS, basically.
I'm not running fast enough. Take it easy.
Hello, I'm sorry. Have you thought about adding a quality of service to the packets or processing so that you don't care if you drop some?
Can you elaborate on that, please?
Have you thought about adding a quality of service to the packets so you don't care if you drop some and don't process them?
So yeah, so we're gonna have like certain logs, some monitoring, alerting on that based on the logs, that if we see any errors, stuff like that. So there's gonna be their dashboards and pager duties and stuff like that. So those things, we're not there yet. We're working on it. So this is something in progress.
Do we have any more questions? Yes.
From your code snippets, it looks like it's basically one Go routine per file that gets dropped in S3.
Correct.
So it's kind of unbounded. So if I just dropped like 10,000 files in S3, do you have something that handles that, or how do you plan on handling that?
Yeah, so we plan to limit number of Go channels. So we are profiling right now different configurations of CPU and memory and how much throughput we can get. And based on that, we need to decide on what we are going with production. This is nothing in production, so we are working on that. So coming up with the config and how many files we want to process in parallel. So we're going to have a limit on that.
Cool. Lucky last question. All right. Please put your hands together.
Thank you. Sorry. One more thing.
One more thing.
We are hiring. Thank you.